are used to think that water as well as materials used in contact with water are stable and they do not interact. This idea leads us to assume that water quality cannot be altered during its transport in the distribution network. Therefore, the distribution network is usually supposed to behave as a passive infrastructure to transport the produced drinking water from the outlet of the drinking water treatment plant to the consumer's taps without any modification. Anyway, research has recently shown that the distribution network is an active infrastructure where water quality could change because of the interaction with materials in contact. One of the most severe events that turned on the light on the importance to consider the interaction between water and the materials in contact with it regards the Flint water crisis, Michigan, in 2014. During a budget crisis, Flint changed its water source from Lake Huron to the Flint River. Due to different chemical characteristics, water from Flint River was aggressive. As corrosion inhibitors were not applied at the time, this resulted in the release of lead from aged pipelines into the distributed water. Sometimes the interaction between water and the materials in contact with it has effects only in terms of organoleptic properties, such as the yellowish color we experience after many days we don't use tap water. Consumers complain about the taste, smell, and appearance of water, but there are no risks. In other cases, the interaction between water and materials could result in the release into water of compounds that can be dangerous for human health, as in the case of the epoxy resins used in recent years to renovate aged pipes by relining, without replacing them and avoiding relevant construction sites. European and national regulations provide the indication to face this issue. Specifically, the recent revision of the European Drinking Water Directive in 2021 contains some key points to increase both the safety of drinking water and consumer confidence in the safety of drinking water. In detail, there are 3 key points to mention. The first key point in the Drinking Water Directive introduces new parameters, updating the list of conventional parameters with some emerging contaminants. Among them, bisphenol A adversely affects the immune system, identified as the critical endpoint in a scientific opinion published by EFSA in 2021. One of the main constituents of epoxy resins is BPA. However, it is important to stress that drinking water contaminated by BPA is not the only exposure route for humans. Even food, especially if packaged in plastic films, represents an important route of exposure to BPA. Consequently, monitoring and controlling BPA in drinking water is of paramount importance to reduce multiple exposure of consumers. About the second key point, for the first time, the directive states that attention must be paid to materials in contact with water, which must not release potentially harmful compounds. This opens up to specific monitoring campaigns, but also to modify technical requirements of materials to be used, both for reactors in treatment plants and for the pipes in the distribution networks, including materials for relining. Furthermore, protocols should be developed to check potential leaching prior to setting of materials, considering the specific characteristics of water to avoid what happened in Flint due to a lack of knowledge. Last but not least, about the third key point, the directive states the importance of a preventive approach in the production and distribution of drinking water based on risk assessment. Indeed, dealing with emerging contaminants, the uncertainty about their presence and effects on human health is high. Consequently, corrective strategies to reduce contaminants in drinking water can be ranked according to their contribution to the overall risk, ensuring that the most effective approach is used. About the migration of compounds from materials to water, scientific and technical literature is available about migration tests, but test conditions are often not comparable or far from the real conditions occurring in the distribution networks, and affecting factors are studied one at a time. For instance, many times the presence of residual disinfectant is not considered, even though booster disinfection is a common practice. The presence of disinfectant can mask the release of compounds with two related drawbacks: a faster disinfectant decay catalyzed by the released compounds causing a lower disinfection performance, the formation of potentially toxic byproducts due to the oxidation reactions with the released compounds. Despite the literature available about migration tests, very few studies refer to BPA released by the relining with epoxy resins and other potentially toxic compounds being epichlorohydrin, amines, and their byproducts formed in the oxidation reactions with the disinfectant, such as chlorophenols, chlorobispheноls, nitrosamines in particular, and DMA. As a matter of fact, comprehensive protocols and tests are not already available when dealing with these emerging contaminants. To match the three key points mentioned before, it is important to combine laboratory testing, migration modeling, hydraulic simulation of the concentration of compounds released into the distribution network, and risk assessment. Regarding laboratory testing, the migration of compounds should be monitored based on water aggressivity and disinfectant concentration, focusing not only on those in the legacy list, but also on those which could directly or indirectly impair water quality, and therefore generate a risk for human health. The experimental results should then be used to develop a generalized model which quantitatively describes the migration in the space of variability of the affecting factors. The hydraulic simulation, through for example the open source EPANET MSX, supports the understanding of the spread of the contaminants released in the network as a function of consumers' water demand, highlighting safe, alert, and alarm areas, and supporting the customization of site-specific monitoring. Finally, risk assessment supports the comparison of potential mitigation actions or different relining scenarios before their implementation. Summarizing, what was considered a standard until a few years ago, i.e., neglecting the distribution network when it comes to water quality, can no longer be considered as such. We need a change of perspective, which forces us to look at the problem in its wholeness, not in closed compartments. Therefore, the drinking water treatment plant and the distribution network must be designed, managed, and monitored as a whole.